Let's take a real quick look at something called the unit step function or the Heaviside function. This function is very useful in practical applications when something is instituted into a problem after a certain phase, like a piecewise function because, well, technically it's a piecewise function. Here's the way it's actually defined. It gets a capital U, and the argument is t minus a. Now, it's a piecewise function. Here's what it says. It says that this thing is equal to 0 until you get to a, and then it's equal to 1 as long as t is greater than or equal to a. So the idea for this, it's really just an on switch. So here's some value a. So this thing has a value of 0 forever until it gets to a. Then at a, this thing jumps up, turns on, and has a value of 1 forever. That's all this function does. Very, very simple function, but it's also incredibly useful. Because you can think about this, especially people that want to go into electronics. This is kind of like flipping on a switch, right? All of a sudden you got no power, you flip on a switch, it jumps up, and then you have a voltage. Now in real life, there is a time span here for this jump, so it actually's got a little diagonal line there in the real world. But for us, it's very, very helpful thing about it. It's just an on switch. Which means this can be very useful for representing really complex looking, kind of like piecewise functions. So let's say we want to represent using a unit step functions. And let's draw something horrible. Let's say I have 1, 2, 3. Let's say that we have 3 functions here. So it's 1, 2, and 3. And I don't know. Okay, let's say that these are our 3 pictures, and I want to represent this mess using our step function. So first off, I have to actually know what these functions are. So let's call the first one f of t. Let's call the second one there g of t, and the wavy one up here h of t. Okay, now the idea for the step function, this is where it gets a little confusing. The only thing this thing can do is just turn a switch on. So where do we want to happen? So since it looks like this thing starts at 0, we want to just turn on the function f of t at 0. So this is going to be a pretty long one across here. So I get u of t minus 0, or just u of t. This will come on at 0. And what value do I want it to have there? I want it to be f of t. So notice this thing has a value of 0 till we get to t equals 0. And then at 0, it gets a value of 1. So at t equals 0, this just has a value of f of t. Now, the next time we want something to happen, here is at the number 1. Now, what do we want to happen at 1? We want f of t to disappear and g of t to start. So to do that, you kind of got to do 2 things. I got to make f of t disappear. Now, I want this to happen at 1, so I know I'm going to use u of t minus 1. Now, notice I'm going to take away whatever f of t is. So notice, what do we have now? When t starts here, so here we're starting at t equals 0, and we're heading this way. At this point, we have f of t turned on. Then we get to 1, that's the number 1 on our number line. Then f of t is on, this is still on, but now this is also on, so that's minus f of t. So notice now, those 2 cancel out. So this piece is on from 0 forever, right? But then at 1, I turn this piece on that negates it. Now, I also want the g of t to turn on there, so also at t minus 1, I want g of t to happen. So here at 1, I'm also adding g of t. So now g of t is now going to be on from 1 forever. Now, the next thing we want something to happen here is at 2. So what do I want to happen at 2? Well, when we're carrying on here at 2, the only thing that's happening is really g of t, because we've already canceled out f of t. But I want g of t to go away because I just want h of t on. So at 2, so I'm going to say minus, because I want it to go away, u of t minus 2, I want to get rid of g of t. So technically, everything that's happening here at 2, let me just so you can see a little better. That's 1 and that's our number line. So at 2, what all do we have turned on? We have f of t turned on, and then minus we turned f of t off, kind of. Then at, we also have g of t turned on at 1. Right, that was also here. But now at 2, we're taking away that, so minus g of t. So you can see, so far, this is all that we have turned on after 2. F of t was turned on from 0. F of minus t was turned on from 1 on. G of t was turned on from 1 on. Negative g of t is turned on from 2 on. Now what do we want to happen? We want h of t to happen at 2. So at u of t minus 2, we want h of t to happen. So plus h of t. And notice if you simplify that, the only thing that we have left on is h of t. And we want that to go on forever. And so if you're ever trying to represent a piecewise function using a step function, always think about when something happens, what the result wants to be. So here, we wanted f of t just from 0 to 1, but then we wanted f of t to go away, so I got to turn it off. You really don't turn it off, you just turn on the opposite, and then turn on what you want. Then I wanted that to go away, so I turned on the opposite, and then turned on the piece that I did want. So our unit step function there is very, very useful for representing complex piecewise functions. Right. Now, of course, we were talking about Laplace transforms. So the biggest question here is, what is the Laplace transform of u of t minus a? Well, by definition, this is the integral from 0 to infinity, e to the negative st, f of t, t. Let's get this out of here. Okay. Let's see. Well, by definition, this is going to be the integral from 0 to infinity, e to the negative st, 1 and 0, t less than a, t greater than a, dt. So the idea here is this is exactly 0. So from 0 to a, this is e to the negative t times 0 dt, plus, and then after a, greater than or equal to a, after a, it's equal to 1. So this will be 0 to, a to infinity, e to the negative st 1 dt. So this first integral is 0. It goes away. So really, all we need to do is evaluate the integral from a to infinity, e to the negative st dt. So integrating that, we get negative 1 over s e to the negative st. Let me set up my limit first. Improper integral. So we were doing the limit, I think we were using b, goes to infinity from a to b, e to the negative st dt. All right, so this is the limit as b goes to infinity, negative 1 over s, e to the negative st evaluated from a to b, top endpoint minus bottom endpoint. So that's going to be negative 1 over s e to the negative sb minus 1 over s e to the negative sa. Now as b goes to infinity, remember we want these things to be finite. We don't want them to go to infinity. So as b goes to infinity, the only way that this goes to 0, because that's where b is at, is if this thing ends up in the denominator. So we need it to go to the denominator, so this would be 1 over e to the sb. Now the only way that it actually ends up there is if s is greater than 0. So as long as s is greater than 0, that's what happens, e to the negative sa. Now as long as that's in the denominator and b goes to infinity, this goes to 0, and we end up with e to the negative sa all over s. So back up to our original one, I'll write it here as our result. The Laplace transform of u of t minus a is e to the negative as over s. Now, this is rather interesting because notice this actually generated an exponential in the s world, and that's the first time we've seen an exponential in the s world, which means anytime we see an exponential in the s world, we can be fairly sure that it's probably going to have something to do with a step function in the t world. We'll take a look at that using something called the second shifting theorem next time.